This is a pressure image. It's from a person resting on a bed with a pressure mat, a flat fabric sensor. Each pixel shows the pressure measured by a square sensing element. We can make out some aspects of the body, the head, the torso. That's probably a foot. But is the person heavy, or are they tall, or are they short? Can you tell where they're at in 3D? It's a bit hard to imagine. If pattern recognition systems could solve this problem, there would be numerous applications, but there's just not much data out there. You can't just go to the internet and download what you like. Our work addresses this. We present a deep learning model trained only on synthetic data that infers the pose and the shape of a person from a pressure image. Here's a photo of the real person to compare.
Hi, I'm Henry Cleaver, and I'm presenting our paper Bodies at Rest, 3D Human Pose and Shape Estimation from a Pressure Image using Synthetic Data. We use physics simulation to generate the training data. Our key insight is that people at rest can be modeled with ragdoll physics to find statically stable poses of the human body. Resting is an important class of human behavior, and understanding it could be beneficial to applications like patient care and assistive robotics. Our work has two main steps. First, we generate a large set of synthetic data, and then we use that to train a deep network to infer human mesh from a pressure image. We use the simple human parametric model to do this. Our objective in simulation is to obtain a large set of resting poses coupled with synthetic pressure images of sufficient fidelity to train a model for use on real data. Current data sets in human pose estimation largely focus on active poses. While these have great diversity, they're quite different from the resting poses that people normally assume. People spend up to a third of their lives in bed, and that's what our work focuses on. Artists have long studied the human form at rest, and these paintings observe the lack of physical exertion and the absence of motion that characterize the subjects. The poses produced by our data have similar characteristics. Now, let's look at how we generate this data set. First, we randomly sample over the body pose and the shape. In comparison to past methods, this provides an unprecedented variety of body poses and shapes that would be extremely difficult to collect in the real world. Next, we find a resting pose by dropping a capsulized ragdoll body onto a soft bed and then wait for it to rest. Then we use a second physics simulation with a non-articulated human mesh in order to find the pressure image. Here are some examples from our data set that represent a variety of postures, including supine, lateral, prone, and many in between. Here we show a close-up of the real pressure mat on the surface of the bed and its simulated counterpart. Our sensor model is based on particle penetration between two layers of particles on the top of the bed. We calibrated our simulation environment using custom calibration objects. We used CMAES to optimize the physics simulation of these objects to match the real objects on the sensor's bed. Our dataset has over 200,000 pressure images and associated resting poses. We have publicly released this dataset along with tools to get started and visualize it. Using this data, we trained PressureNet, a deep learning model that inputs a pressure image in a gender and outputs a human mesh estimate. PressureNet consists of two modules, each of which contain a CNN, an embedded simple human model, and a novel PMR component. PMR stands for Pressure Map Reconstruction. This component differentiably reconstructs pressure maps, which promotes consistency between the input and the output. We have released the code for PressureNet along with our best trained model. Here we show PressureNet in action. The first stage computes a coarse estimate which doesn't quite match up with the ground truth. Then, based on the spatial residual between the original pressure image and the reconstructed one, Module 2 fine-tunes. We trained PressureNet using only synthetic data and tested it on both synthetic and real data. We collected testing data from 20 people on a sensorized bed in both self-selected and prescribed poses. We also released this data. We ran a number of ablation studies. Notably, ablating PMR made the largest difference. In summary, we introduced a method to generate synthetic data of bodies resting in a bed with a pressure sensing mat. We used this data to train a deep network with an embedded model of pressure map reconstruction and found that this model generalized well to real data. Now we'll show you some more results.